Hello, my name is Jacob Blazejewski. Thank you for stopping by to learn more about our poster. Imagine I hold an uninflated balloon in my hand. It starts off as this shriveled piece of rubber, but as soon as it expands. This change in shape is known as an evolving surface. Evolving surfaces and evolving curves appear in many scientific models of physical phenomena. One example would be constructing a 3D MRI scan of the brain. To do this, many 2D cross-section scans of the brain are taken in various directions. In each of these cross-section scans, the region of the brain must be identified in order to stitch all the scans together to form the final image. One way to automate this process is to grow a curve to encapsulate this region. The evolution of the curve can be modeled by a partial differential equation, a PDE, which requires a numerical method to solve. Our group uses the meshless radial basis function finite difference method to accomplish this goal. The RBF method relies on having known function values in a scattered data set. A radial basis function is then centered at each of these nodes. A linear combination of the radial basis functions is taken to obtain the interpolant of the underlying function. We combine the RBFFD method with the tensor formulations of surface operators to perform calculations relying solely on information provided by the nodes on the curve itself. These error plots demonstrate this approach converges. That is, can successfully calculate various operators, such as the normal direction of a closed curve and the Laplace-Beltrami operator. The method is easily adapted to compute other operators as well. Being able to reliably calculate normal directions was imperative as we approached evolving curves. Our first test case was to shrink the unit circle down to a point. We obtained consistent results with a benchmark problem for various initial node sets. The current focus of our group is on the next test case, merging circles. Once that test case is resolved, we will be able to evolve a broad class of closed 2D curves. Then we will generalize our approach to surfaces in 3D. Thank you so much for your attention. And if you're interested to learn more, feel free to email myself or another member of our research group. Bye now.